So am I audible now? My voice is audible
Yes, yes, perfectly.
and the screen is also visible, right?
Haha.
Okay. So we are going for that failure theory. So in failure theory, like different topics, different theories are there, like maximum principal stress theory, maximum shear stress theory, maximum strain energy theory, maximum strain energy theory, like that. Distortion energy theory, distortion energy theory, all these type of theories are there. So we are going to study one by one. Maximum strain theory, maximum strain theory, like that. So we are going to discuss all one by one. So apart from that theoretical part, like whatever derivation is there in the book and all, apart from that, we are going to see the graphical approach, like how we are going to feel that meaning, like physical meaning, what is happening actually in the, if we plot all this thing in a graph, like more circle with detail in detailed discussion, we did that, like that we are going to discuss. So whatever part is there, like in theoretical part, I have taken some question, and that question is totally related to theory only. It's not a numerical problem. It's related to theoretical part, and that theoretical part, in that so many concepts are there. So we are going to discuss that concept first. So it will be beneficial because that question itself is a part of theory. So that's why I have chosen that question. So after that, we will discuss that maximum principal stress theory, maximum shear stress theory, and the maximum distortion energy theory. These three parts I will try to finish today. But before that, we are going to solve two problems, and that two problem is related with your related with the failure theory only. And out of this five, any two of them or three of them will be there in the question, like maybe maximum maximum shear stress theory or maximum strain theory or like that. Anything can be there. So the thing is that one more point I want to add, like whenever you are reading maximum shear stress theory in the gate examination, what they are giving sometimes, like in here they will give like that, and here they will give some name of scientist here, like Rankine theory, Gosset and Tresca theory, like Rankine theory, Gosset and Tresca theory, distortion, one Mises theory. Like that, they will give some name. So, like, nothing but a name. Just this scientist had Rankine and this thing that and theory he has used, and means simply like he has analyzed that thing. So you people, I suggest you people remember that theory, like name, like maximum principal stress theory. This was given by Rankine. So sometimes people are calling in the Rankine theory also. This one. Okay. Similarly, maximum shear stress theory. This is also known as Gusset and Tresca theory. So I just wanted to tell you, like, just remember this name also, because they may ask which theory is which one, and just cross. You have to cross it, like this theory may be this one, this theory may be this one, like that. So 1 or 2 marks they can ask, because in history, if you check, these type of questions are there. Okay, so I mean, just be updated with that also. So you go through that Einstein theory, Gaussian and classical theory. It's just a name. This is nothing but a name. Whatever it is here, the same thing. Okay, one Mises theory, rank theory, so all these things. Okay. So coming to the point, like you have a question in front of you, and you just have a look at this question. Consider the following statement related to maximum shear stress theory. Okay, maximum shear stress theory. This is also uh, this guess theory, graphic, whatever you are pronunciation. So this is Gaussian and Tresca theory. So related to this theory, they have given some 3 points. Okay, this theory is well justified for ductile material. Okay, well justified for ductile material. Point number one. It gives accurate result for the state of stress of shear, pure shear in which a maximum amount of shear is developed. This is the second statement. Third statement, these all three are related with this. They are just they are giving the three statements related to maximum shear stress theory. The result of this theory differ from the experimental result for material having large difference in elastic stress, limit in tension and compression. Okay. So I just want to make sure that this theory, this theory, Vasan and Resaka theory, we are applying for ductile material. And why we are applying for ductile material also I will answer. But that is not a part means that we are not going to discuss here because that is a big chapter. Why we are going to this big I will explain. Means after this question I will explain why. But for now, I'm just telling you for now, you consider this point like maximum shear stress theory people generally we are using for ductile material and that this is best suited to ductile material. Similarly, like rankine theory are there. So that is generally we are using for brittle material. So these two or three points will be there in your textbook also. This material, this theory is used for ductile or brittle or like that, this material. So this theory we are using for ductile material. I will tell you. I will explain why I am telling like this is used for ductile and brittle also. Okay. So this option is correct. Okay. Then the third option, the result of this theory differ from experimental. Yeah, this is also correct. Like this result theory differ from experimental result from the material having elastic stress, elastic limited tension and compression. So in this, you people have read about the History's laws and all. History's laws. Anyone of you?
Yes, sir.
What is that? Can you explain?
So some of the stress will be regaining in the body when we are loading and unloading. It will form a loop.
Yeah. Yeah, it will form a loop. And suppose, simple thing I'm telling you, experimental result if you have, and there is a lot of difference in elastic limit in tension and compression. That is nothing but your, suppose this is your graph, strain system curve I'm telling, this is, suppose this is strain and this is stress. So you're just going like this, okay, like this. So suppose this up to here, whatever it is, up to here, your limit point is here. This is in tension. Suppose this is in tension. Same thing if you are going in compressor, if you are going in compression, so suppose this is 100. What they are telling in the third point, this is suppose this is 100 megapascal. And in compression, it is going something like 500 megapascal in compression. Like a material is there, and this is a material, and you are elongating it in this direction. Okay, so I am telling you like yield point elastic limit means yield point is 100 megapascal. So after that, there will be plastic deformation. Before that, if you leave the material, it will regain its original shape. That will be elastic deformation. So elastic deformation material, then the material regaining its original shape. In plastic deformation, they will not regain its original shape. Okay. So if you are going above, then plastic. If you are going below, then elastic. So I am telling you this is the elastic limit. Now, same condition I am giving, like same material is there, and you are this time you are compressing this. You are compressing this. Okay. And in compressor, material is also different, elastic and plastic. Now I am taking in compression that yield point is your 500 megapascal. 500 megapascal. So this is large difference. Means in tension and compression, material is not going to behave same way. Means in tension, whatever material response was there, that's not similar to the compression. And for this type of behavior, shear stress theory is not applicable. Not this type of theory, shear stress is not applicable. So what they are saying, this result for theory differ this theory differ from the experimental result for material. Yeah. So then what will happen? So this theory, the result will differ. In tension, the shear stress theory will give some other result, and in compression will give some other result. When there is a large gap, when there is a large gap. Okay. So this statement I just want to explain you. You little bit to dig this statement. Okay. What I am right now telling just a statement. I am making a statement without any reasoning. I am just telling you. If material is going, material having elastic limit, there is a large difference in elastic limit, in tension and compression. Then what will happen? This theory, this result or this result of shear stress, maximum shear stress theory differ from experimental result from that material. So then in this question, only this thing it gives a accurate result from the state of pure shear stress. Pure shear stress in this maximum amount of shear. So this is correct. Okay, this is correct. Because they are telling there is a large difference. They are telling like there is a large difference. So this is correct. Yeah, it will be. So in the third statement, it gives accurate result from the state of stress of pure shear in which maximum amount of shear is developed. For this is here they are making a wrong statement, and why they are making a wrong statement like this theory, maximum shear stress theory, and whatever they are telling here that the state of stress of pure shear, you know pure shear, what is the mode circle? It will be like that. Okay, the center is here. It will be the center 0 point for a pure shear stress. This is a pure shear stress. Okay, you have noticed all this thing or not? Like this is a pure shear stress. This is this is what pure shear stress, and here this will be the maximum limit of your tension and compression. I will explain. Like this will be the tension and this will be the compression. Like normal stress. This will be the shear stress. Like this is the general case. So this will be tension here also. Like this point is giving you maximum normal stress and display. So I have just explained this thing. I'm not going in detail with this part. So this is the mode circle for the pure shear stress. Okay. So in which amount of so what they are telling in which maximum amount of shear is developed. So this is not correct. This statement is not correct. Okay. What they are telling which of the above statement is not correct. So this will be the only option for you. So here in this question, I don't think so. You get what I'm trying to basic fundamental. This is just for you if you have studied well, very well studied that maximum shear stress theory, then you will figure it out. Okay. So for now, just digest this question. I will come to that basic part also. Okay. So yeah, here I have just taken some slide of maximum shear stress theory. This that point is I told you now like this question is already a part of theory. So only theoretical part will be there. So whatever we are going to do that is a qualitative analysis. So this theory is due to the Gaussian and Tresca and therefore it's known as the Gaussian and Tresca. Why I have taken that point because I just wanted to tell you little bit in depth about that maximum shear stress theory. So yeah, here this scientist name are there. So because of their name, that is called Gaussian theory. Okay. According to this theory, the failure of a material will occur when the maximum shear stress in a material reaches the value of maximum shear stress in a simple tension at elastic limit. This is also a point. Each and every point I will prove and I will show you graphically and explain you. Okay. So I'm just telling you the bold point here for your objective question. So maximum shear stress in the material is equal to the half difference between maximum minimum principal stress that you know already. Like if you want principal stress sigma 1 and sigma 2 and you have already derived this thing also. So this will be the maximum. Only I'm telling you sigma 1 and 2, not 3. Plane stress strength. If 3 is also there, then the max of all these 3. So this will be your tau. Okay, you know this thing. You have derived this. So I'm not going in depth of this. So this theory is uneconomical for pure shear because it provides excessive safety for pure. So why this is unsafe means why we are why we told like in question also like pure shear it provide excessive safety factor. Like what is the meaning of this statement? Like suppose you are designing a material and your maximum shear that a material can tolerate or your structural member can tolerate is 100 megapascal. Okay. And you are this is the thing. Okay. And you are calculating for a pure shear and according to your theory, you will get some 500 megapascal, and you are, according to your theory, you are telling this is our this thing, maximum limit. We will have to uh, like what I'm telling. Sorry, this is your maximum limit, maximum limit, and you, according to your theory, you are calculating this value 100 megapascal. So you are far below than your maximum value. So if you will check the factor of safety, so you have five factor of safety. Means 100 megapascal you are applying, but that network can sustain up to 500 megapascal. So in this theory, maximum shear stress theory, in the condition of pure shear, this type of error is coming. Okay. So this type of error is coming. So that's why they have written excessive safety factor for the pure shear. Okay. And also again, this is a straightforward statement, like this theory is well justified for ductile material, well justified. This is just a statement. They are not giving any reasoning. I will tell you the reasoning also. So for now, you just digest this statement. This is well justified for a ductile material because they can ask objective question. Okay. So you should read about this thing. Which theory is applicable for which material, ductile material, viscoelastic material, molecular material, all these things. You just go through it. It means it is indicating they can ask this type of question. The meaning of this statement is this. Okay. Okay. So the graphical representation is hexagon. So this part, I think if you have derived that formula of maximum shear stress, what is that maximum shear stress, like sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, sigma 3 minus sigma 1 by 2. If three stresses are there, so this mod of all these things, so maximum this will give you your maximum shear, maximum value of shear stress. If you plot graphically, it is going to come like a hexagon. It's also a part of that theory, maximum shear stress theory. So when we will discuss that alone, like maximum shear stress theory, when we will discuss, we will plot that hexagon also. Okay. So for now, you just remember the graphical representation is hexagon for this theory. This theory is hexagon, and this is applicable for ductile material. Like that, if you will make notes, then you will remember all these things. Hexagon, ductile, and this for pure shear stress, it is giving excessive factor of safety. Okay, this 3 point is very important about this theory. I'm just why I'm going like that. Just only my intention is to brush up your concept, whatever you read till now. Okay. So, like whatever it was there, so same thing I have just written here in the theoretical part, like maximum this value, you know, if two stresses are there, sigma 1, sigma 2, sigma 3. So, how we are getting this? That already we have developed. And we have discussed in very first lecture itself. And factor of safety also we have discussed here, like whatever load you are applying and what is the maximum limit that like if you divide with whatever load you are applying with the maximum, then you will get some value like 2 times, 3 times. That is your factor of safety, nothing but. And just don't confuse about which part you are going to put in numerator and denominator. Always a higher value is in numerator and lower value is in denominator. So lower value is your. So people are making mistake here. That's why I am repeating. Lower value is your nothing but whatever load you are applying, and higher value is the maximum limit. Okay, so higher value is always top, and lower value is down. Okay, so that is done. Okay. So again, this is a very simple question. Okay. So if you have doubt, you can ask after this question. So again, identify the name of the theory of elastic failure with a given description. And you just point out whatever point I am making. Like all these questions are like theoretical part. So you just make just point out where I am putting more space, more focus I am putting like hexagon, ductile material, not effective for pure shear. All these points you make, because these are very important points. They can ask like In one statement, they will write maximum shear stress theory. And you can put four or five statement like here, and they will confuse. Like one is correct, one and two is correct, only two is correct, one and three is correct. Like that, they can confuse. So you make a strong understanding of all these points. Okay, the time material, return material, graphical path, like the right time theory, if you are going with the right time theory, that is rectangular, maximum shear stress theory, that is hexagon, all these things, distortion energy theory, like elliptical path, all these things, you just make a point wherever I am stressing that statement, okay. So this is the question, like identify the name of the theory of elastic failure with the given description. Yeah. The portion of strain energy again, this previous question also intentionally I had taken to explain the maximum shear stress theory. Here also this question is related with the maximum like distortion energy theory. This is related with the distortion energy theory, but they have asked this question in different way. There are no very distortion energy theory in the question. So again, this question they are created just to just your understanding, like how deeply you have studied this theory, maximum discussion energy theory and external energy theory. So if you have studied, then easily you can figure it out. The question is given, and they're asking the portion of strain energy. Okay, the portion of strain energy. What do you mean by portion of strain energy? It's some part of that strain energy. Okay, some part. So sorry. So some part of this energy. So what do you mean by some part? Definitely there will be some part means 2, 3, 4 like that. Something will be there. Like 100% energy is there, 50% is going somewhere, 50% is going somewhere, 60-40 is going somewhere. Or maybe you can say 40-40-20% like that. So that we don't know right now. Okay. So the portion of system energy producing change in state of the element is assumed to be completely responsible for the failure of the material by ending. Any one of you, do you know like what is the meaning of this statement? This statement. Any one of you, can you explain? I just wanted to. Why I'm asking because I have explained this theory in simple stress strain class. I have explained this theory.
Sir, is the option 2. I mean, the energy needed for the strain will be only taken, so it should be shear strain.
Any other statement you want to make? This is a straightforward answer. The answer will be maximum shear stress energy theory. I just want to know any other point which you can make from this question. Like I told you, na, whenever a question somebody is throwing towards you, your intention should be like how much information I can get from that thing. So any other statement can you make? So many things are there in this one line. Anyone? Any other person? Anything. You just make a statement. Maybe you are wrong, maybe right. I don't care. Just I want to know like you should speak something. Something you can. Right, wrong, don't forget about that. Whatever understanding you have about this statement, whatever you are thinking, I want to know where are you right now. I just want to know so that I can figure it out and it will be easy for me to start with, like from where I should start. Anything? Yeah,
Max,
somebody is telling
maximum strain energy.
maximum strain energy theory. Okay, you people are confusing. So okay, okay, very good. So I will explain. Okay. So yeah, somebody told like option two, maximum shear strain energy theory. This one. But the point is not to get the answer. Point is what is happening here. Okay, so I have written some statement here, 4 point. You can read this statement. What is this? Okay, so and you can relate this thing. So here, portion of strain energy. So whenever a body is there, some shape is there, and you are applying some load, or you are twisting, you are compressing, you are giving some tension, some shear, anything, bending, some load. You are means something you are applying. You are loading that body. So what will happen to that body? Always you have two components. One is deviatory component, deviatory. Okay, means that is you can say hydrostatic. And I have already told you meaning of hydrostatic and deviatory. I just want to. I will be happy if you will tell what is the meaning of this. Anyone? Hydrostatic means you are compressing the body. Every point you are putting the equal stress, equal pressure, you can say. So hydrostatic just like this body is there, na? This will become same shape, it will become like this, a smaller size. Same shape, it will become like that. Distortion means you are changing the shape of the body. You are distorting, like you are this shape was there and you are making something like this. You have compressed it and made like that, like that. So you have two parts, shape change and size change. Size means you are whatever shape was there, you are with that, you are maintaining that size, but shape, but you are changing the size. Means you are reducing it, you are compressing it. So if like suppose you have simple body like that. From this side you are applying same pressure. From here also you are applying same pressure. Here also same pressure, same pressure. Okay, and you are compressing it, and I'm telling you this object is compressible, so this will become a smaller and smaller. So shape is same, that is rectangular or cube you can say, but that size is you're going down. So two part, always you have two part, one is hydrostatic and one is distortion. Distortion is changing the shape, and hydrostatic is changing the size. So don't confuse about this, and keep this thing in mind. Whatever energy you are putting in the body, there is always a two part of that energy, hydrostatic and distortion. Okay. So hydrostatic means simply you are equal pressure you are putting at every point on that surface of that body. So simply, if somebody will tell what is the hydrostatic stress, if you have sigma 1, sigma 2, and sigma 3, three principal stresses are there. So always hydrostatic stress are average of these three. Okay. And in some book or textbook, they are writing sigma P. P means pressure. So equal pressure you are putting at every point of that body, everywhere. Okay. And one is the total energy theory. So in this question, what they are telling, change in shape. Now you tell me, hydrostatic or distortion?
Distortion.
Distortion, correct. So if you have studied like that, size and shape, hydrostatic and distortion, two component, sigma p, then easily in 1 second you will figure it out what will happen here. So change in shape means distortion energy theory is going to will play here, play a role. So in distortion energy theory, what is happening? We are using simply like a strain energy theory only we are using, and in strain energy theory we are finding total strain energy sigma t. We are finding total strain energy sigma t, and in this energy there is two part, one is your distortion and one is your hydrostatic sigma. Hydrostatic I can write like that, two part. So if you will go with this, so in this, if you have to find out what is the value. So if you will, here I am going out of the question. The question is done here. Change in shape. This will be maximum shear strain energy theory, and that is related with your distortion. In distortion, you have a maximum shear strain only. Okay. So the answer is this done. But out of this question, I am going to tell you something. When you are going to calculate maximum. Sorry, a total strain energy. This is your sigma t. The total strain energy, how you will calculate? Simple, like you are writing 1/2 sigma 1 epsilon 1, 1/2 sigma 2 epsilon 2, 1/3 1 by 2 sigma 3 epsilon 3. Here you are writing in terms of principal stresses, means you are finding this total strain energy in terms of principal stress. Principal, I am telling you. So here there is no shear component. You are not finding anything in terms of shear. So don't be confused. I will explain that part also. So for now you are finding principal stress in terms of principal stress. So you will get, and if you put all the value of sigma epsilon 1 epsilon 2 epsilon 3 in term of sigma, then you will get a big expression like 1 by 2 e in bracket sigma 1 square plus sigma 2 square plus sigma 3 square, like that you will get one expression. So that is your maximum strain energy. So in that whole part of that energy, you have two part. Suppose maybe this will be 60%, this will be 40%, or anything else. So what I am telling, if you will subtract this from this, you will get this. This is the easiest way to get the distortion energy. What is the value of distortion energy? Okay. So what I'm telling, you can try that derivation. I will give give you some hint. So, let me drink some water. Okay. So here, coming back to the question, like in this statement, you can read it is also known as the maximum energy of distortion. So here, change in shape. Here, distortion energy theory. So I told you this is related with distortion energy. The one myself. This is the scientist name. So you can figure it out now. Everywhere that scientist name is coming, criteria consider that diameter of and all. That is another part. So you remember which scientist name is related with which theory. That is also important part. That this statement is telling that thing only. Okay. The portion of the strain energy producing change in state of the element is assumed to be completely responsible for the failure of material by yielding. Okay. So this statement, what they are telling, completely yielding. This theory provides the best agreement between experiment and theory, and along with the Tresca theory is very widely used. So this is the one of the best theory which give the not exact we can say, but very much close to the experimental and the theoretical part. Okay. So generally people are using maximum this thing. If you have a member and you are designing, you are putting some load and you are trying to find when this member will fail, when this member will break or distort, something will happen. When you are generally people are using distortion energy theory. According to this, you have loading system, your geometry is given, so you can calculate how much energy it will absorb before failure, and you can put subtractor safety, and according to that you are going to apply your load. So this is a practical thing. Okay. So for theory, you have an important part how you are going to calculate this distortion energy theory. What are the component of that total energy theory? Hydrostatic and distortion. The third part is shape and size. Fourth part is one Mises criteria, and the fifth part is best agreement between experiment and theory. This is for your GATE examination. All this can be asked in the question in the exam. Okay. So coming back, I'm just trying to uh, recapitulate everything whatever I told. Like Gusset and Tresca theory, it was maximum shear stress theory, and we are telling like this is also GT theory, applicable for ductile material. Okay. For pure shear, it is overestimating. For pure shear, what is happening? It is giving a big factor of safety. Means okay, you got that point now. So for pure shear, you must be careful. Like say one statement we made now. for uneconomical for pure shear because it provides excessive safety. Okay, uneconomical, pure shear, uneconomical. So this is a very important point. Okay. Now coming back to your distortion energy theory, distortion energy theory. So this is also known as Born-Mises theory, BMT. Like that, you just make some trick for you so that it will be easy for you to remember. And this theory is coming from the total strain energy. Total strain energy. Okay, you can write total strain energy. There are two parts of that total strain energy. One is your shape change. One part is going to change the shape and one part is going to change the size, and one is going to change the shape. So when size will change, your volume will change. Okay. So this is also called hydrostatic. And hydrostatic, you are compressing the object or something. So your volume will go down. Okay. Like so all dimensions are going down. Shape will remain same. Okay. So size change and shape change. So in shape change, what you are doing, you are distorting the object. Simply you are distorting. Okay. So you will apply some shear to distort the object. Okay. So this part is also known as distortion energy, and this part is known as the energy required to change the size. Okay, hydrostatic you can say hydrostatic. Okay, and next thing is this is giving a good agreement with theoretical and experimental data. Okay, so a good agreement. This is statement you can make with experimental and theoretical data. I'm writing in short because I just want to give you a hint, like you just remember it. Okay. So this point from this two theory we got. Okay. So the point is we have just find out what are the truth about that theory and few something related to one Mises criteria like shape and size and that is little bit less, but the maximum shear stress theory just we have made some statement. We have not given any reasoning why this is happening. We have just made a statement to figure it out to solve that objective question like the kind material on economical pure shear like that. Okay. So the next thing, uh, I'm just planning to discuss all this theory in detail with some derivation also and some question also. So for this recording part, I have taken two questions. That's what I have solved. Next recording part, I will take some question and that will be related with the numerical problem. Okay, numerical problem. And that before going to that numerical problem, I just want to discuss that theoretical part. Okay. So let me stop this recording.